The first speaker of the morning session is Ken Taylor, and the title of his talk is Random Turing Triangulations Are Not Geometric. Right?
Thank you very much for the invitation to speak. So I'll tell you what Viering triangulation, I'll give you a construction of Viering triangulation a little bit later in the talk. Right now I just want to start with sort of a canonical object and ask some questions. Okay. So we'll see. Okay, so let's think about starting with a pseudo-nonstop homeomorphism of a surface. Okay, so just given that piece of information, Hegel associated to that a canonical ideal triangulation of a certain method. Okay, so there's an ideal triangulation. And I'll call it tau sub f, so that's the pseudo-nonstop, of what I'll call f circle. So what is f circle? F circle, I'm going to take the pseudo-nonstop, so it has singular attracting, so it has two singular foliations. Okay, and I'm just going to puncture the surface at the singular foliation. So this is S punctured at the singularities of the stable and unstable foliations of the pseudo-nonstop. Okay, so I take my pseudo-nonstop, I puncture it. Kaz is also talking. I take my pseudo-nonstop, I puncture it at the singularities, and I produce from it the mapping torus. So this is just the mapping torus of my pseudo-nonstop F. So 0, 1, and then from the top to the bottom. Okay. Alright, so here we go. To recap, first of all. I'm given a pseudo-nonstop, and I produce an ideal triangulation of the manifold I get by puncturing the surface at the singularities and then the mapping terms. Okay? So this is some canonical construction. So what do we have? Okay, so we have this manifold. So this is, I'll give a construction of this later. Okay? What do I have? I have this manifold. I called it that. Okay? And it has two pieces of information. So first of all, it's hyperbolic. So we heard why it's hyperbolic earlier. So when I puncture S at the singularities of F, I still have a pseudo-nonstop mapping class. And so this manifold has a canonical hyperbolic structure. Now, in the manifold, this S might have been a closed surface. Right? So the original mapping torus is maybe a closed through manifold, but this one now has cusps. It's hyperbolic structure, defined volume hyperbolic structure. And it also has this this ideal triangulation. So two canonical structures, this ideal triangulation, which I'll call tau. Okay, so at least they're canonical given the pseudo-nonstop. Okay. So what it makes sense to do is I have a hyperbolic structure, I have this triangulation. Are they compatible in the right way? You could ask, are they compatible? And when Hegel introduced this construction, he asked that question. He asked it in the correct way. He says, is this triangulation geometric? So that's the way of asking the question. So this is the question of Hegel. So of course, I have to tell you what it means to be geometric. It means that the triangulation is compatible with the hyperbolic structure, but let me say what it means. I'm going to say it in a couple of different ways. I don't worry about it. So tau is geometric. Yeah. So first let me just say one way of thinking about it. So I'm building my cusp 3 manifold by gluing together ideal tetrahedron. Okay. That's what the triangulation is. So it's geometric if I could give each of those ideal tetrahedra the shape of an actual hyperbolic tetrahedron, such that when I glue them together by pairing the faces, sort of they glue together coherently to give the hyperbolic structure on the 3 manifold. Right, so that's like the intuitive notion of what it should mean to be geometric for the two the triangulation to be compatible with the hyperbolic structure. So to think about what could go wrong, so we should think about, in order to understand the definition, maybe we should think about what could go wrong. Right, so I have this triangulation. It's some topological triangulation, and it sits in my hyperbolic 3 manifold. So if the edges of the triangulation are essential, essential arcs in the 3 manifold, I could just think about pulling them tight to be geodesics. right? And so what could go wrong with the triangulation when I do that? Well, I pull it tight via some homotopy, and the problem is, well, maybe that homotopy isn't an isotopy, right? So when I pull it tight, maybe some edges pass through other edges, and maybe a tetrahedra that's sitting there, topologically, when I go to pull it tight to be geodesic, kind of turns itself inside. Okay, when it does that, it kind of gets the opposite orientation of what it should get. Right, my manifold, my original manifold, has some orientation on it. It's oriented. S is oriented surface. Someone assumed that in a previous talk. Something like that. So when I pull it tight, what can happen is, I guess I should have said S is finite type. Okay. So when I pull it tight, right, a tetrahedra can get an opposite orientation. Right, so I could just define geometric in this way and say tau is geometric if when you realize how in the hyperbolic metric each tetrahedra is positively oriented. So no tetrahedra sort of turn themselves out, turn themselves inside. Okay, so we'll see this, maybe how this gets used later in the talk. Okay, so
Sam, the idea here just refers to the fact that these points, the vertices are out at the cusp or something.
yeah, so right, in the hyperbolic structure that's what's happening. So an ideal triangulation in general is I'll just realize my manifold as have a homeomorphism to a simplicial complex with the vertices. That's what it is in general, and then what I could try to do is realize those tetrahedra as actual hyperbolic ideal tetrahedra, and then see if the hyperbolic structures glue together. Right, so if you know, familiar with Thurston's gluing equations, this says there's a solution to Thurston's gluing equations where each tetrahedra. Okay. Great. So so we have canonical triangulation. We have this canonical hyperbolic structure. They should. Why wouldn't they? One another, except sadly, the answer is no. So the answer is no. Exclamation point. The Viering triangulation is not always. So no means is how maybe the question should be always geometric. I mean, certainly when Hegel introduced this this construction, he computed a few examples, and for his examples, they were geometric. And there's other reasons why, if you took like a once-punctured torus or a four-punctured sphere, they are always geometric. Okay. So when he asked this question, there was reason to believe maybe they are geometric, and the answer is no. So this is due to Hodgson, Isa, Siegerman, who actually produce examples of non-geometric Viering triangulations. So they produce an example of a geometric of a Viering triangulation of one of these manifolds and show that try to realize the triangulation in the hyperbolic structure, you'll necessarily have negatively oriented. Okay. However, there are lots of examples of these Viering triangulations that were geometric, and they even point this out. They did computer experiments, and it seemed like in sort of low complexity examples, a lot of them are geometric. And so with Dave Fuder and Will Worden, we were interested in that question. How often are they geometric? And so we just write the theorem. Okay, so here's the theorem. So again, this is joint with Fuder, myself, and Will Worden. Okay. I'll start right here. So let's let S. So I'll tell you what S can do. So it's finite surface, such that there's when the genus is greater than 1, there's no conditions other than not the torus, but once punctured torus. Okay. If it's genus 0, I have to write down kind of a funny condition, and I'll explain why later. Okay. So if genus equals 0, then I want the number of punctures to be greater than or equal to 5, so I already explained why that's straight. And odd. I'll explain why. I mean, the theorem is also true for n equals 6, and 8, and 10, and like any number you give me, but okay. So I'll explain why. I'll explain why. I'll explain the bottom later on. Okay? Okay, so then I'm gonna have to use a different board, but okay, so let's let Wn be a simple random walk. So just random walk on the mapping class group of my surface, one of these surfaces. So the theorem is true more generally. I just want to keep it simple.
What's simple?
Simple random. So I'm going to take a generating set on the mapping class group. I'm going to give each give each generator uniform weight. Yeah, and then I'm going to take a random walk with that measure. So it's more generally true, but then I don't have to say something about the support. Okay, I'll put the conclusion right here. Right, then the probability that so first I should say something. It's known from work of Igor Rivin and Joseph Marr that if I go far enough out on the walk, with probability approaching 1, these random elements will be pseudo-ionized. Okay, so I could apply the Agol's construction. I could look at the Viering triangulation. So it makes sense to write tau of WK. This is the Viering triangulation, this triangulation that I will soon explain, for this pseudo-ionized element. And remember, it takes place on the manifold. What happens when I puncture Wn at the singularities, and then I build a mapping twice. So the probability that this triangulation on this manifold is geometric, okay, goes to a 0 as it goes. Okay, so this is the theorem I want to explain. What it says is should
K goes to infinity, or is it?
K goes to infinity. These should all be K. The problem is I would always use N, but then I use N here already.
Right.
So should have used it here. Okay. Right. So the point is their example is these examples they constructed particular example. So, but this is generally the thing. Okay. So actually, the rest of the talk, I'll give the definition or construction of a Viering triangulation, and I'll say some properties of Viering triangulations, maybe why you should care. But then really for the rest of the talk, I want to explain why this theorem is true. It sort of breaks up into a bunch of different independent steps. So I think at least say something about it. Okay, so that was part 1. Maybe part 2 is Viering triangulation. So, like I said, these were introduced by Agol in 2011. So since then, the notion of Viering triangulation has been generalized. So everything I'm going to say is sort of the idea he had originally in mind, and so now maybe these are called layered Viering triangulations, but I won't say any more about them. Okay, so if maybe you're familiar with Viering triangulations in a more general setting, everything I say will be about layered Viering triangulations, and if you're not familiar with them at all, just forget the word layer. Okay, so these were introduced by Agol. The way he had originally conceived of them is you start with your pseudo-Anosov, okay, and what he does is he finds a canonical invariant train track splitting sequence, and then he uses the train track splitting sequence to sort of layer tetrahedra on top of the surface S in a way that matches the splits, and from that he gets this triangulation. So I'm just saying that very, very quickly because I'm going to give a different construction later on that's much more suitable for proving this theorem. Okay, so maybe I just want to say some things that are known about Viering triangulation. So, right, I'm trying to, I want to prove a theorem that says there's some disconnect between the combinatorics in the Viering triangulation and the actual hyperbolic structure. However, there are lots of other places where the Viering triangulation really tells us something about the manifold. So even though this theorem is kind of a negative result, there's lots of reasons why we should still care. So let me just say why. There's a lot of names here. So first of all, I'll just write these triangulations, the Viering triangulations. Have positive angle structures. Okay, so what is this? So I mentioned before Thurston's Gluing equations, when you can solve Thurston's Gluing equations with positively oriented tetrahedra. Then you have your hyperbolic structure. There's a certain relaxation of those equations, and the existence of a solution to that relaxation is called having an angle structure. And what it is, you just think of it as some weakening of the hyperbolic structure. So sometimes you could start with a positive angle structure and use that to find the actual hyperbolic structure. But it shows some sort of connection between this triangulation you start with and the actual geometry you're interested in. So there's lots of names that should go here. So Hodgson, Rubinstein, Siegerman, Tillman. That's one team, and then also Fuder and Garrett. So I don't know why it matters. You're not going to be able to read these names anyway. Can't say that in every talk. Okay. So that's one connection to things maybe you're interested in. Another connection is there are strong connections to Cannon-Thurston maps. Connection to the Cannon-Thurston maps. So these are fiber manifolds, and so there's a Cannon-Thurston map for the fiber, right? And what Guillotot shows, so this is Guillotot. Guillotot shows us the way the Cannon-Thurston map, sort of the way it sort of traces, the way it gives you a space-filling curve at infinity can be recorded via the combinatorics of the Viering triangulation. So there's connections to geometry. There's also connections to combinatorics of the Viering triangulation is connected to the structure of subsurface projections and what you see at the level of the arc graph. So I'm just going to say connections to subsurface projections. So we heard about those in earlier talks. So this is and Yarvinsky. Okay, and then there are also, so I was going to ask Saul if I should mention this before the talk, but you got in late. So there's also connections to pseudo-nonstop flows, which is work that you have with Henry Siegerman. So I'm going to put that here, to pseudo-nonstop flows on the manifold. I'll just put Siegerman. Okay, so there are connections to the hyperbolic structure via Cannon-Thurston maps, to the structure of the arc complex and subsurface projection, and structures to the dynamics. So the Viering triangulation somehow sees all of these things in some sense. Okay. Okay, but let's actually see the definition. A definition. So what I want to do is, instead of giving Egel's original definition in terms of train tracks, I want to give a construction that's due to Guillotot that he used to establish this connection with Cannon-Thurston. And this is how we're going to sort of see. So the ultimate goal, I guess, is, besides the theorem, is we're going to see how if you vary elements of the construction a little bit, and that'll be clear what that means in about 3 minutes, how the Viering triangulation actually changes. So how is the Viering triangulation, this triangulation of manifolds, dependent on the input? Okay, so let's think about Viering triangulations and talk about Guillotot's construction. So what do we start with? Let's start with, let's fix a quadratic differential Q on a Riemann surface X. So we heard about these earlier, so I'm going to think, so quadratic differential gives me a singular flat structure on my Riemann surface, so maybe I'll just draw a picture over here. Maybe not covered yet. So, right, so there's some vertical foliation of the structure. So this is a schematical local picture of what's happening at X. So here I have, I'll call the vertical foliation F plus, and then I have this horizontal foliation F minus. I'll come back to this picture later. Such that, so here are the conditions that I need in order to get started with the construction. So first of all, the singularities of the quadratic differential, singularities of Q, to happen at the punctures of X. Okay. So all the singularities happen at punctures. So maybe you start with any quadratic differential on any Riemann surface and puncture it at the singularities, and you have that first condition. The second condition is I want no horizontal or vertical saddle connections. Okay, so this just means no Euclidean line segments, either vertical or horizontal, joining punctures. Okay, so these are the two conditions. So these are natural conditions if you think about where this picture comes from. Maybe I should say that. So where do things come from, like in this setup I have here? Remember, I think about starting with maybe a pseudo-submap, okay? And then I'll let X be the Riemann surface I get by puncturing. So given a pseudo-knot submap, I get a quadratic differential. Choose any quadratic differential, that determines the Teichmuller axis for F. So I have my quadratic differential, and then I just take my surface, the surface that I get, the underlying complex structure at that quadratic differential, and I puncture it at the singularities. So that's like my setup. Okay, and when I do that, I have these two conditions. So I punctured at the singularities, so the first bullet point is free. And the second bullet point comes from the fact that I started with the pseudo-knot stuff, so it doesn't have vertical or horizontal saddle connections in the beginning. Okay. So this is maybe, keep this in mind, but this is sort of a general setup. Okay, so now what do I do? Yeah, I see now the shadow problem. Okay. Okay, so what do I do? Let's look for rectangles. In this picture, let's look for rectangles. So singularity, free rectangles. Fancy R for that. So what does that mean? So I have this Euclidean picture. Locally it's Euclidean, right? Locally this is just correlation by vertical and horizontal lines. So I can draw like a tiny rectangle. Here's a rectangle. Okay. And by a rectangle, by a singularity-free Euclidean rectangle, what do I mean? I mean it's a Euclidean rectangle within the local structure, and such that the vertical sides are contained in the vertical foliation, and the horizontal sides are contained in the horizontal foliation. But it's the picture you expect to see. So there's one right there. And what do? Is let's look for maximal ones. So obviously I could have really, really small ones, and I keep blowing them up until I can't anymore. Right, so maybe I start right here, and I blow it up until it gets to this guy right here. And why can't I extend it anymore? Well, I can't extend it anymore if I run into singularities. So remember, these are actual punctures of the surface. Okay, but I'm just going to draw some dots. So I can't extend the rectangle anymore if I run into the singularities. Right, so I'm going to let R be a maximal singularity-free rectangle. Okay, so there's one right there. So this is maybe my R. And I'm going to associate each maximal singularity for rectangle. So this is happening in X. So in X, this might be an immersed rectangle, but don't worry about whether it's immersed or embedded just for right now, or during this talk. So I extend my rectangle till I can't anymore. Okay? And then I'm going to associate to that maximal rectangle an ideal tetrahedron. Okay? And it's the tetrahedron you see. So what does that mean? It means, so think about taking the convex hull of these 4 points, okay, and then thicken it up a little bit to get a tetrahedron. Right, I'm going to thicken it up in an oriented way. So I'm just going to use the rule that the edge, the diagonal joining the top to the bottom, sits above the diagonal joining the two sides. Okay. So
And this is where you're using the fact there's no saddle connection?
that's right. So there's a new saddle connection. I have one singularity in the interior of each edge. Yes, that's exactly right. Okay, so to the singularity for rectangle, I'm going to associate just an abstract ideal tetrahedron I'll call P sub R. Right, so this,
Could the saddle connect the singularity be on the corner?
no, because then you could extend it either to the right or up.
Ah.
Yeah. TR is tetrahedron, right, ideal tetrahedron. So abstractly, just for each maximal rectangle, I think about giving myself an ideal tetrahedron, and I'm going to name it TR for each maximal rectangle. Okay. And now the triangulation is just glue them together in the way you can. So write that down, and then maybe setting right there. Okay, so then maybe I'll start by defining tau tilde. Okay, so tau tilde, this is the Viering triangulation. I'll tell you in a second. So tau tilde maybe, tau tilde, I can specify the quadratic differential. All the data is contained in the quadratic differential. Is the ideal, simplicial complex obtained by gluing these tetrahedra together along faces. So let me just tell you what I mean by along faces. So two faces, what color did I use? Two faces of the ideal two faces of these tetrahedra correspond to triangles in my surface. Right? So a face of this blue tetrahedra, one face of this blue tetrahedra is this triangle right here. Does everyone see this triangle facing me right here? Right? So if two tetrahedra are glued together along a face, if those two faces give the same triangle in the surface. Okay, so let's just see an example, and that's what I mean. Okay, so I pointed out this triangle right here. The triangle spanned by these 3 points. We see that's the face of the tetrahedra I drew. So if it's going to be a manifold, there better be another tetrahedra somewhere. And where is it? I just extend this. I extend this rectangle downward. So what I do is I'll draw another singularity-free rectangle for you. Right here. And maybe it stops because I hit some singularity right here. And so the other tetrahedra is this one. Okay? Okay, so the definition is really simple. It may take some time to digest to see what's actually going on. For right now, I want to point out one very important fact. Maybe the most important fact for us going forward. So all I have right now is I have an ideal simplicial complex. That's what I've told you. And I've given you the formula to construct it. I've given you the formula. So let's record one important fact. What are the edges of this triangulation? Whatever the triangulation is. So sigma is an edge of this triangulation, tau tilde, if and only if on the surface, sigma's a saddle connection. A saddle connection is just a Euclidean line segment joining punctures, in this case. It's not just any saddle connection, it's a saddle connection that spans a maximal rectangle. It's a saddle connection that spans a singularity-free rectangle. Okay, so sigma is a saddle connection spanning a singularity-free rectangle. Okay, so this definition does take a lot of time to absorb. But just notice from the picture, what are the edges that I use to create this triangulation? Those are saddle connections, and those saddle connections are in this triangulation if and only if they span a singularity-free rectangle. You can see the rectangles in it. I use Euclidean rectangles to say what an edge is. Okay, let me just say a couple more words about how you go from this, what this object is, and then I'll maybe pause for questions if there are any about the actual construction. Okay, so at this point I'm just going to give some facts. What did we just construct? So these facts are, this is Garateau's constructions. These facts are verified in Garateau's paper, but they also come from Ian Hagel's construction. So first of all, maybe fact 1 is this object, tau tilde. So a priori, it's just some ideal simplicial complex, but it's actually is an ideal triangulation of, my starting Riemann surface X cross R. Okay, so what you actually see is, this picture right here this is X, and I'm stacking tetrahedra on top of X. Okay, and what you could show is that the way the tetrahedra is stacked together, it actually gives an ideal triangulation of X cross R. So this is fact 1. Fact 2, so this is the triangulation. Fact 2 is that if this whole picture came from a pseudo-Anosov, then the whole construction is invariant under the action of pseudo-Anosov. So that's more or less clear from the construction. So if this whole construction came from this little setup right here, so if we started with one of my punctured pseudo-Anosovs, and X was the Riemann surface of the punctured surface, then what does F do? F acts on the foliation. F acts on the surface, my actual pseudo-Nassau homomorphism, acts on the surface, right? It permutes the punctures, it sends leaves to leaves, right? And so it sends maximal singularity-free rectangles to maximal singularity-free rectangles, right? So it just acts on the tetrahedra, it permutes the tetrahedra, and it preserves the face relation. So what do I say? So this whole picture gives me a simplicial homeomorphism, capital F, from X cross R to X cross R, preserving the triangulation tau tilde. And so what I can do is I can look at my X cross R mod out by the action of F, and what do I get? I get my original mapping torus on the punctured version of F, and an ideal triangulation with ideal triangulation, what I'll call tau, right? Tau sub Q. So I start with tau tilde, which is on X cross R, but then I realize that there's a depth transformation that is simplicial with respect to this triangulation. And so on the quotient being the manifold that I start with, this punctured mapping torus, I get an ideal triangulation. Are there any questions about the construction? It does take some time to absorb. The point is it's an ideal triangulation. It's got from a singular flat structure on my surface. And maybe it's abstract, but at least I know exactly what the edges are. The edges are the saddle connections that span these singularity-free rectangles. So that's how I work with it. Okay. So with about 15 minutes left, 20 minutes, something in between there. Okay. So section part 3 is the overview of first. So I wrote out 4 steps. Step 1. So in step 1 we're going to see why we don't get all surfaces, or at least, yeah. Okay, step 1 is kind of interesting, I think. Step 1 is, if I'm going to prove this theorem, so the theorem is a theorem about each individual surface, right? I start with a surface, and then I prove something about the Viering triangulations starting with that surface. If I'm going to prove the theorem, the way the proof works is I need to start with, so fix S, one of these S's, I need to start with a non-geometric Viering triangulation, some non-geometric Viering triangulation on that surface S. So the proof won't produce, well, once I have one, the proof will produce many, but I need one to start. Right? So for instance, Hodgson, Isosigerman produce one. It's not the one we want. But I need at least one for each surface. So let me write that down. So what do I need? For each S, as in the theorem, we need some meaning one, pseudo-Nassau on the original surface, such that 2 things are true. 1, I need the associated quadratic differential, where the Teichmuller axis of F, to be principal, to lie in the principal stratum. So what does it mean? I mean, what does it mean? What do I mean by the quadratic differential being principal? It just means it has a certain singularity structure. So what do the singularities look like? So these are singularities in the original surface S before I puncture. So S has a material singularity, a singularity that's actually there. I want it to be a 3-pronged singularity. Okay. Or if S has a singularity of puncture, I want it to be a 1-pronged singularity. So that's just what it means for the quadratic differential to be in the principal stratum. Okay. So this is what I want. And 2, this is step 1, I want the associated Viering triangulation on my punctured manifold to be non-geometric. So step 1 of the theorem is to have an example. So in this case, even for the examples of Hodgson, Isis, Sigerman, of course the second condition is true because that's what they were interested in. But the first condition wasn't true, so we couldn't actually use that example. And we need an example for each surface. Okay. Luckily for us, there's a lot more tools available now to construct Viering triangulations and see whether they're geometric. So the main tool for us to get an example is Mark Bell's program Flipper. So Flipper will compute for you the ideal triangulation, and then you could feed it to Snappy, and Snappy will tell you, and then we could do other things to make this rigorous. But we'll essentially tell you whether the triangulation is geometric or not. Okay. And then there's a little bit more extra work to do to make sure that that computation is correct. Okay. But of course, doing that, they'll give you finitely many examples. Ask the computer to do it finitely many times. And then you need tricks to get the rest of the surfaces. So there are some covering tricks you could use. When covering tricks don't work, there's some computations using the Thurston norm that you could use. And those tricks work for everything except punctured spheres. And then for punctured spheres, you need to come up with a different idea. So we use different kinds of branch covers. But the branch covers we use, like for each surface where we verify these two conditions, we'll get certain branch covers of it, but not all the punctured spheres. So that's what I said before. Of course, for the 6 times punctured sphere, we look and we do an exhaustive search using Flipper and Snappy. We find the example, and then once we find the example, we can run the rest of the argument. But we don't have a general process that works for punctured spheres. So it's just this first step. It's a lot.
Could you say just a sentence about the Thurston norm trick?
Yeah. So for instance, think about how you do this for once punctured surfaces. So the way we do it for once punctured surfaces is we find a 3-manifold with one cusp. One cusp is important because you know when you change the fibration, the singularity structure of the foliations doesn't change. So if you use punctured spheres and you try to change the fibration, the singularity structure changes, and you're not in the principal stratum. So we find one. To do this search, we find one 3-manifold that works for all once punctured spheres, and then we know something about
Surfaces.
what's that?
One punctured surfaces.
Once punctured surfaces. Yes, once punctured surfaces. Works for all once punctured surfaces. And then we actually use Regina to tell us what the Thurston, we do tricks to actually find what the fibered face looks like and things in the boundary of the fibered faces. Great, that's step 1. So I'm not going to say anything more about step 1. Okay. Step 2, let's move on for more. I'll keep the theorem statement on the board. Their names right there. So, step 2 is where the random walk stuff comes in. What we're going to do is use some work of Dodger and Marr. It's going to tell us a little bit about, along a random walk, what can we expect about the quadratic differentials. Okay, so to back up, right, we have our construction. The construction comes from quadratic differentials. And the ultimate goal is, let's think about, well, how, if I change the quadratic differential a little bit, so this will be step 3. If I change the quadratic differential a little bit, how does the Viering triangulation change? How does the construction change? And what we'll see is there's a precise sense in which if you have converging quadratic differentials, then the Viering triangulations will converge. Okay. Right, and maybe just to tie it together, what's that have to do with the hyperbolic structure? And then we use sort of known results in the literature to say that the hyperbolic structures are converging too. And then all we have to do is kind of relate what's happening with the Viering triangulations to what's happening with the hyperbolic structures. So that was a summary of steps 3 and 4. Okay. But step 2 is going to be, what does the random walk give us? Okay, so I'm just going to write down a lemma, and it's a lemma that we kind of extract from work of Dodger and Marr. So it's not precisely the way it's stated in there, but just a little bit extra work will get you this lemma. So let G be an element of math vector, pseudo-Nosov, and principal. So it means the singularity structure of the foliations is like over there. Okay? And I have my random walk from before, so I have this random walk, what the lemma says is there exists a capital N, so let's say it this way, for almost all, I'm going to use N now, for almost all sample paths in my random walk, there exists a capital N such that if N is greater than capital N, the nth step of my walk, well, I already said the nth step of my walk is pseudo-non-stop. With probability approaching 1, this is a stronger statement. This is pseudo-non-stop. What Gadramar show in their paper is not only is it pseudo-non-stop, but it itself lies in the principal stratum. Okay, principal stratum. So this is a principal pseudo-non-stop. And, okay, so this is maybe the extra bit, but it really is sort of in their paper. There exists a sequence of elements in the mapping class group such that, what do I have? I have my quadratic differential for the nth step of my random walk. Okay, so what does this mean? So I'm being loose with notation. What does this mean? This means I'm going to make a particular choice of quadratic differential along the tabular geodesic for W. Okay. And then what I'm going to do is I'm going to translate it to the right spot. I'm going to translate it to the right spot using this sequence. And the point is I can find a sequence such that after translating, this will actually converge to the quadratic differential for my starting guy, G. There's an intuitive notion of what's going on here. It has to do with the Teichmuller axes getting fellow traveling for longer and longer, and translated the Teichmuller axis for G. But this is what I want. This is telling me the random walk will produce for me some collection of quadratic differentials that converge. I'm not going to worry about the translation, right? Because in translation, when I build the mapping torus, kind of corresponds to a remarking, and it won't affect whether things are geometrical. Okay. So what do I have now? Now I have my converging quadratic differentials, and that's great. So what I say is, well, what happens? So this is all of step 2. What happens? Converging quadratic differentials should tell me something about these triangulations. Any questions about this? It's surprising if you haven't thought about it before, but Okay, the next step is, how do I?
Oh, Sam, I have a question.
Yeah.
Should it be a subsequence of you?
No.
It's an actual.
No. I'm choosing these guys.
Yeah, those are.
Absolutely not. No, I'm choosing these guys. No. I can choose translates of my random geodesic so that it fellow travels a particular different translates of my original geodesic for longer and longer amounts of time. No subsequence.
The convergence is slow. Right? It may take a while. It takes a while before you get an extra.
I don't know, it's something they're got it here. Yeah.
It takes a while.
I don't know how fast. Yeah.
So the point is, you don't know where along the axis W.
No. That's where these guys are finding for me
But-
where
but-
along the
but
axis.
it's finding- I see.
That's right.
So you're finding like G's showing up somehow.
That's right.
Sequence, various
Right.
places.
If you just thought about it symbolically, right? I'm finding like the spelling, yeah. But then there's actual Teichmuller like geometry to do to make sure that what you think would happen symbolically actually happens.
The convergence is probably fast. It's a random walk.
That's why I didn't say anything about it. Let's not worry about whether it's fast or slow. Irrelevant. Okay. Should I? Okay, I'll do this. So what do I have? Now let's just think about me having these converging quadratic differentials. What can I say about these Viering triangulations in the next 5 minutes?
That's what it's done.
Yeah, that's why I need. I understand something. Yeah, so let me just, so I won't put up lattice and stuff. So what's the point is, so when these quadratic differentials converge, what does converging mean? Okay, I don't know. But in particular means that the metrics converge, right? The metrics given to me by the quadratic differentials converge. And what we could do is we could use the L1 metric, which is just like horizontally plus vertically, to actually say whether an arbitrary arc in the surface is an edge of the Viering triangulation. So step 3 is that I can metrically determine when an arc is an edge of the Viering triangulation. And so if I can metrically determine it, then nearby metrics, in some sense, determine nearby arcs. Okay, so I'm going to write this like in the most informal way possible. Qi converging to Q in the space of quadratic differentials, and we have to, of course, restrict to the subspace of quadratic differentials that have Viering triangulations, but that's not an issue, is going to imply convergence of the Viering triangulations. Okay. What does this mean? Intuitively, what it means is if I take my limiting Viering triangulation tau, it's the one I get from the quadratic differential Q, I fix some big compact subcomplex. Okay. And then far enough out in the sequence, that compact subcomplex lives as a subcomplex of the Viering triangulation of the approximates. Okay. That's what it will mean. And in order to do that, I need to be able to metrically determine when an edge, like what it means to be an edge of the Viering triangulation. So I have this surface. Now I'm looking on the punctured version of the surface. So there's some process by which we go from the convergence in the type Miller space of the unpunctured surface to convergence of the punctured surface. And so I'll sweep that under the rug. But then what I get is I get the corresponding sequence on the punctured surface. And I need to tell you what the arcs are. So maybe I'll just draw the picture because it's a nice picture. Okay. Like, I have an arc on a punctured surface. Is it in the Viering triangulation or not? Metrically. Can I see metrically? Okay, so here's the picture. Okay, so I like this notation. A of tau is the subgraph of the curve complex, arc complex, consisting of Viering edges. What does that mean? That means I look at my arc on the surface. Is it a saddle connection spanning a singularity-free rectangle? Right? You can tell just by looking at the surface with that quadratic differential. Okay, so how do I tell? Okay, so I'll just show you the picture. So if I actually have an arc with a Viering triangulation, what do I have? I have this picture, and then some kind of rectangle, some kind of Euclidean rectangle. This is living on the surface. And what does it mean to be a Euclidean rectangle? It means there are no punctures in the rectangle. So let's call it A. Just right now it's some arc. What does it mean to be in the edge set of the Viering triangulation? So there's A. It means, like, pretend you are going to try to write A as a concatenation of two other edges. A1 times A2. What does it have to look like? Well, A1 is going to terminate also at a puncture. But there are no punctures in this rectangle. So it's got to leave the rectangle. So here's A1. A1. And then, of course, A2 means coming back. So, if you would do this, you have to do it precisely and carefully. But just in the picture, you see if I tried to write A as A1 plus A2, I would have to leave the rectangle. The rectangle is like the L1 convex hull of these 2 points. And so what that means is the L1 length of A is strictly less than the L1, the sums of the L1 lengths. L1 length means take the horizontal distance to the vertical. So in the Viering triangulation means strict inequality. How about not in the Viering triangulation? Okay, so the other case, if A is not the Viering set, what's the picture? What's the picture that goes with that? Okay, so you should really draw this picture in the universal cover, but we're not worrying about those issues. And then what does it mean to not be in the Viering triangulation? It means to one side or another, I can't draw that maximal half rectangle, which is a triangle. So what I can draw is like these smaller maximal rectangles. Okay. And when I draw these smaller maximal rectangles, it means I see punctures right here. Okay. And so what I can find in this case, when I'm not in the Viering set, I can find these other arcs, A1, A2, A3, where the sums, the L1 length of A actually does equal the sums of the L1 lengths of the AIs. Okay, so you might say, well, why is it actually the sum? So then you have to go to the universal cover and you have to verify that this is actually the picture you see. This picture is actually, in previous work with Yair, we verified that this is the picture you see in the universal color. Right? In particular, this little polygon between the A and the A1, A2, A3 intersects each leaf of the vertical or horizontal foliation exactly once, which verifies that the concatenation is still at L1 shapes. Okay, so in the remaining 30 seconds, what does this tell me? This tells, so this is in words. In words, this tells me informally that as the quadratic differentials converge, the Viering triangulations converge. Really what you would do is you'd set up an open neighborhood of Q, such that once you're in that open neighborhood, you see as many edges of the Viering triangulation as you want. Okay? And now, in the remaining 30 seconds, you have to relate that to the hyperbolic function. And how do you do that? So you're lucky because there's only one thing you can do. The only thing you can do is I have the quadratic differential. That gives me the vertical and the horizontal foliation. And I have the solution, the resolution of the ending lamination conjecture, right? There's a unique hyperbolic structure that's going to give me those ending variants. So this is Brock, Mayer, and Minsky. And moreover, by Leininger and Schleimer, that dependence is continuous on the subspace I'm looking at, where these ending laminations are, where these guys are ending laminations, that association is continuous. And so what do? What I do is I say, okay, I have this convergence of representations. How do I relate the representations to the triangulations? It's simple. Each endpoint of a tetrahedron, each endpoint of an edge, is a parabolic fixed point, is a fixed point of a parabolic element. Convergence tells me that the parabolic elements converge. And so in hyperbolic space, the endpoints converge. So the summary is I have the Viering triangulations converge. And in the representations I care about, the actual shapes, the hyperbolic shapes of those tetrahedra are converging as well. So if I started as something where I saw a negatively oriented tetrahedra, then a nearby tetrahedra, and in the approximates, I would see essentially the same tetrahedra. I'll wiggle one endpoint a little bit, and it also has. Okay, so that's it. Thank you.
Any questions for Sam?
Yeah.
So I was trying to follow this step 3 and I was confused. How does the step rule out the possibility that you could limit the Q with where in the sequence there are singularities near the boundary of the supposed rectangle? In other words, for the QI, you might have a singularity that prevents that rectangle from existing, and then the limit that kind of fixes the rectangle.
So I'm not exactly sure what you're asking. So we have the convergence on the punctured guide. So this is happening all on the punctured surface.
Right?
And then you're worried that in the limit, well, in the limit, I mean, we're assuming that is an edge in the limit.
Yes, so it's an edge in the limit, but maybe it's not an edge in the approximates because in all the approximates there's a singularity preventing the rectangle. So that's a rule that-
In all the approximates, there is some, well, let me put it over there.
Well, maybe this point over here on the right is getting close to the right edge of the.
Don't you need like the no horizontal or vertical?
Well, that no horizontal or vertical is going to say, in the limit Q, there are no horizontal or vertical segments. So this is not coming into here. You're worried about this coming into where? Draw me a picture there.
Can't, maybe it's-
Yeah, so a particular worry might be this singularity comes and hits this horizontal edge, but as Andy said, that can't happen.
I was worried about
Limiting
the
quadratic
points
differential has a
inside.
Viering triangulation.